Okay. Really, I can't give any better introduction than what Sean gave. That's really a nice introduction to what this is, so I'll just directly jump into the details. So basically, this was actually presented by Kevin, as you see the name there. He's from the SQL CAT team, Customer Advisory team. For those of you who don't know, CAT team, it's a Microsoft. It's an elite team in Microsoft. One of the several duties of that team is to help customers with large SQL installations. When they have problems with highly profile and highly mission critical SQL based applications, they go and help the customer and make things right. So as part of that, so Kevin did a lot of these large SQL installations around the world, and he compiled some of those. Obviously, we cannot do everything, but he compiled some of the most interesting ones, and he gave a presentation internally to our Microsoft folks. And at least a dozen times I said, "Wow, really?" Because myself being in several of Microsoft folks being within Microsoft also, we don't know some of these major projects. Yes. What's that?
Did you give
I did. Yes. So it'll be interesting for everyone to know, what SQL can do. I mean, there is still that misconception in the field saying, oh, SQL can't scale. Oh, SQL is not enterprise ready. And even worse, oh, SQL is a toy database. You can't use it for bigger mission critical applications. So I asked Kevin, okay, I want to do this. I want to present it to my SQL user group here so they know what's out there. So they kind of get impressed, and they can do similar things in their environments as well. So I took the permission. So with that permission, I'm using this his own deck. I made slight modifications, but it's basically his deck. And all right. So okay, one more thing. So like I said, most of these projects are not something that I was directly involved. Maybe indirectly. In some cases, some in planning stages. So I'm just a messenger here. So don't shoot me. All right. So here are the session objectives. Learning about some of the largest custom SQL Server projects that SQL CAT team helped various customers. See the techniques, how they scale, all right, and how they do HADR. We'll talk about a little bit of that. So basically, the takeaways from this is, after this, when you go out of this room after this, you should go with that mindset that SQL can scale and SQL is enterprise ready. That's my intention here. And I don't want to go too technical because stop me if I'm going too technical and taking a long time, because if you give me time, I'll let you sit here throughout the night. So please don't. So I'll try not to go too technical. I want to go. I want just to cover. My intention is to cover those highly profile, the largest custom SQL Server projects. All right. Here is the top statistics we have so far. I mean, this was a little older slide, so there may be more improvement since then. But largest single database we had, with the customers that we know, is 100 terabytes. Single database, OLTP. Largest table, 1.5 trillion rows. And if you ask, what's that?
Slow down. That's pretty technical.
Okay. Okay, then let's change it into the size. 20 gig. Is that 20 terabyte? Is that too technical? Okay. So the database, the single table size is 20 terabyte. Wow. Yes. Wow. Biggest total data for one application, 88 petabytes. I mean, across several databases, across several servers, but for one single application, SQL-based application, the database, the total database size is 88 petabytes. Highest database transactions, 130,000 transactions per second from Perfmont. If you use that transactions per second metric. Fastest I/O subsystem, 18 gigabytes per second. Yes, wow. Fastest real-time cube, millisecond latency. The real-time cube where you have the data available immediately as it is entered into the database system. We had millisecond. It used to be like 5 seconds and so on before, but we achieved millisecond latency. That means within the millisecond of receiving the data, you have your cube ready to generate the report and give it to you, generate the report for you. Data load for 1 terabyte is 30 minutes. Now the asterisk is nothing to worry about. I mean, that is the that is the highest. I mean, we have in labs, so that is a real-time, real-world. So I only want to talk about the real-world examples. I'm not talking about the labs, what we do in labs. In lab, we could load 1 terabyte data in 7 minutes. That's how fast we could do. And I'll show you. Actually, I'll explain you a little bit how we could do that. But in real world, in customer environments, the data load was 30 minutes. Largest MOLAP cube, 24 terabyte. So, can anyone beat this? Yes.
I can't beat it. I was just curious. I know you can't give out the company names, but what industries are you taking your 100 terabyte largest database?
We'll talk about that. In some cases, I can actually give you the names also. We have a PR relations where we would say it's okay to give the names. Okay. In cases like, for example, that 88 petabyte, I cannot give the name because the customer themselves said, we don't want our competitors to know how cheap we are able to do this using SQL servers. So they didn't want us to give the name. But, so here are some of the names you're asking for. So in some cases, I don't have names like the larger LTP because we did not get any approvals on using the names. But in some cases like BVIN, we are going to talk about BVIN. We're going to talk about Hilton Corporation and some of the others. So I don't know, maybe some of these companies either you worked or working or worked before or no. But the slide is going to be with you. I'm going to leave the slide so you can go through this. I don't want to go through each and every one of those companies there. But we are going to touch some of these major customers and how they did it. Well, so how is it possible? Okay, we saw this table with, really unbelievable numbers. How do they do that? I mean, is there any magic in there? Absolutely not. There is no magic. It's all some things probably you already know, you're already implementing. It's all using the same techniques like, compression. The first and foremost, compression, I mean, I know there is still some misconception there. Compression is something that actually slows you down because we think about in terms of actual compression. I gave several talks in case even I gave on one of the SQL Server days, I gave a talk on database compression where we can see, where you have the I/O bottleneck, the compression is going to actually help you to improve your performance while reducing the size of your database. No doubt it's going to put a little more pressure on your CPU, but most of the time when you have the I/O bottleneck, this compression is actually going to help you improve the performance and help you scale. So compression is something that we recommend very much. And of course, table partitioning. Everybody knows table partitioning. So we are going to talk about how you can use the table partitioning to scale out and scale up at the same time. And partition views, the old school partition views, in conjunction with partition tables, you can use partition views to improve scalability. And of course, service broker for async transactions, where you don't want to tie up your databases with those transactions. You can do async, and we have one case study of a large retail company who is using this service broker to get benefits. And of course, file group and file management. Sean talked about it, in almost, of course, every DBA training he gave, and everybody knows, how the file groups and file management is going to help improve the scalability of your databases. Now, soda. Anyone knows what soda? No, not the one you're drinking there. Anyone? Soda?
Service-oriented database.
Thank you. Yeah, services-oriented database architecture. So, so this is not any feature. It's a technique. Basically, this is one of the techniques you can use to improve the scalability of your database applications. SODA. We'll talk about more of that. Service-oriented database architecture. DDR, not Dance Dance Revolution, for those gaming folks there. Anybody? DDR, left press, come on.
I would have said it before you said Dance Dance Revolution.
That's exactly why I have that thing, I know. DDR, it's data-dependent routing. Routing your data connections based on data. to scale out. So, you have your data across multiple servers, how you can, how you can make your application intelligent enough to know where to go and get the specific data. So that is data dependent routing. So we talk about, and of course, scale up and scale out. Some customers like to go scale up, some go scale out, some go mixed. But all these are going to, we're going to talk about different techniques to scale up and scale out to help you with this. Okay, so first we'll talk about the data warehouse case studies. There are 4 case studies I have, and so these are the techniques they used. In one case they used very fast disk subsystem. We'll look at the details of those fast disk subsystem, how they got that. And in one case they used analysis services with write back to rollup technique. And in one case, scaling out analysis services and reporting services, and last but not least, analytics before OLTP. So these are part of the data warehouse, and we'll look at each one of these studies. So the first one, 80 terabyte reporting system. So I cannot use a name here. It's a large electronics company. Make your guesses. So they are using a large reporting system with 80 terabyte of data. So they have this data coming in from various sensors in their manufacturing line, and they're holding 36 months of data at any given point of time in their database. And of course, they have these file groups and file management, one per file group to hold the data. But their the heart of their system, if you see, it's a simple architecture there. It's a simple active passive cluster. Of course, no doubt there are like bigger 20-core box servers, but the main heart is their disk subsystem. It's a VMAX. It's a very new EMC VMAX SE. They're using 3 of those, and if you look at those details there, they have like 20 ports. So if you see the 20 there coming from the boxes, so they have 20 ports coming out of their each of those boxes. Each one is 8 gigabits per second, load balanced with power path. So that means 20 times 8 effectively, right? So that's kind of bandwidth they have from the system. And then it's finally going into the storage where they have this is one box. This shows one box how it is stored. Basically, each box has 88 450 gigabyte 15K RPM disks with RAID 5. Well, RAID 1 plus 0 or 0 plus would have been given a better, almost double the throughput what they're getting. They're getting 2.8 gigabits per second, which they think it's big enough. But after seeing there are others which are achieving higher, but for them it's okay. It's okay. You don't go overboard, right? You want to balance your expenses versus what your requirements are. So they're happy with this. They have a RAID 5 with 80 data disk with 20 RAID sets, and they have in each VMAX SAN they have 5 data LANs. So basically 4 RAID sets per LAN, and they're getting 2.8 megabytes per second, which is 2.8 gigabytes per second, 2,800 megabytes, and they're happy with that, and they're able to run all the reports they want with minimal latency for their 80 terabyte system. Yes, sir.
Is this your data dependent routing?
Uh-huh.
Are they using that data?
No, not in this case. In this case, it's one single server. Data dependent routing, when you want to scale out, it's basically mostly like a scale up. Right? They scaled up their I/O subsystem basically. So it's nothing very. If you look at the previous slide, so it's a simple active passive 2 node cluster there, active and standby. But their main heart here is because you will agree with me if I say most of the time what we see is I/O system is where you will start seeing bottlenecks. So if you have properly configured I/O system, you can handle your load even with an 80 terabyte data system. So there's one single 80 terabyte database, and they're still able to serve their requirements for their reporting needs. So that's one thing. Then LG Electronics. Here I can give the name. So they use analysis services with high scale write back. Let's see how they do it. LG is actually, it's a very big business. They have 115 business worldwide, 80,000 employees. So what they wanted was a demand forecasting system for their LCD division. For LCD TVs, they wanted to forecast their demands. So they wanted to build this analysis services system to do that demand forecasting. And then, guess what they choose? They're choosing to SQL Server 2008 or 2 to do that. Not Oracle, not other anything, but they use they're choosing SQL Server 2008. And, with that, they got the benefits of improved transaction performance, adaptable BI with effective investment, I should say, quote unquote, there, increased usage value. Let's see how they did that. This is, this is basically how they're. So if you see, what they have is called trickle feed. That's why they have the write back. Write back for those, not very familiar with the SSAS concept, analysis services. Write back is basically where you can, you have your cubes, which are effectively read-only, but then you can have the data coming in. You can store it in a separate table, and then you can aggregate when you're running reports. The server can take the static data from the cube and the data that is trickling into this write back table, combine them, and give you the reports out. So you don't have to. So that's one way to reduce the latency of you don't have to wait for your cubes to be processed. You don't have to wait for your data to be. You don't get a day old data or a couple of hours old data. The data is coming in. It's a trickle feed coming from different sources there. The black boxes there you see on the slide, ERP, SCM. So the data is coming in, and they take that. They use these write back partitions. What they do is they actually they partition their cubes. They partition a combined, a mixed partition of MOLAP partition and ROLAP partitions. So all the static data, which is old, they put that into MOLAP partitions. All the most recent data, which is still coming in, which is still being updated, they use ROLAP partitions with write back approach to get the performance, balanced performance with their cubes. All right. So again, this slide is going to be there with you. You can go through those details, but the key factors here are they use write back, like I mentioned, and they use a custom application written by WISE, a local ISV. The database size is not very big, 5 terabyte, but the queries are very complex. The way they, any given point of time, there are only 11 concurrent users. There are 3,500 registered users, but there are only 11 concurrent users. But still, because the complexity in nature, the way the reports, they retrieve huge data sets to multiple users. So the query response is 30 seconds, but they're able to achieve this by using this combination of MOLAP and ROLAP with write back. As you see there, they maintain 5 years of history in the cubes, the MOLAP and ROLAP combination. So they're basically, there are 6 divisions, and so they have about 2.4 billion records into the table. And the data increases daily by almost up to 5 million cells, anywhere from 100,000 to 5 million cells. So it is huge. It is, it's very, it's growing. I mean, the 5 terabyte now, I'm talking maybe, it went into, I don't know, maybe 7, 8 terabytes since the time we had this slides built. So that's how. So the write back mechanism they use with the MOLAP and ROLAP combination, they're able to achieve this. They're able to give the data with the 30 seconds, less than 30 seconds query response time with their 5 terabyte database system. Hilton Hotels, my favorite, everyone's favorite. Room forecasting system. So they have this room forecasting system, obviously, which is also built on, actually this was built, this is actually a bit of dated, but we still wanted to use because these are one very jewel in the crown, so to speak. They are on Windows 2005, Windows 2003 with the SQL Server 2005. There's planning to migrate, but right now they're still on that, and they're still able to achieve very good numbers with that SQL 2005 and Windows 2003 combination. They use full suite of products, SQL, AS, IS, and RS. They scale out AS and RS. Basically, their motto is if you need to more capacity, basically they are using the scale out mechanism. So if you want more capacity, add another server for AS and RS. Obviously, if you are talking about real OLTP, the data, it may not be as simple as just adding another server. But when you have the data sitting in a server, and I'll show you the architecture in the next slide, and when you have AS and RS that is talking to these databases, it's relatively easy for you to scale out your AS and RS servers, simple as adding another server and making your application talk to those servers, use the load balancing. I'll talk about that. So there are basically 40 to 50 concurrent users, but still they're very complex. They run very complex queries, very large data sets, so it's very crucial for them to get the better performance. There is actually a case study. If you don't know, Microsoft.com has a case studies website where there are several case studies on very good, all of our highly profile and highly visible projects. So I strongly recommend you to go to that. There is a link for this specific case study, but there are also other case studies. We even have case studies based on SQL Server 2012. Believe me, there are customers who are already implementing SQL Server 2012. In fact, I have one of those case study as well. So this is basically the architecture, how the Hilton architecture is. So if you notice, the one in that gray, slight gray boxes there are the reporting services and IIS servers. And what is in the middle layer, the server with the globe icon there, those are the analysis services. There is no data on those. They're just simple analysis services which go talk to the cubes underneath. So basically the COLPF MS8. Do we have a pointer here? We don't. Do you have a laser pointer? Okay, never mind. So that the COLPF MS8 is the I'm sorry. So that's the main cube where the data, the cube resides, and all these servers connect to that, point to that to get the data out. So anytime they want, and if you notice on the top, if you really squint a little, you can see the HLB, hardware load balancer. So they use hardware load balancing to use any of these servers. The hardware load balancing basically, when the request comes, it looks for whatever the server that is free, that is not busy, and the request will be sent through that. So anytime if they want to add more servers, they can add or remove. So anytime the load is more, they can add more servers to the IAS boxes there, or reporting services, or even the web services, because they're all simply, the data is actually residing down in the boxes there. There is nothing really the data residing there, so it's very easy for them to scale out their analysis services and reporting services machines. But what happens here is the database server on the left side there, CSQL FMS1, that's their main database server. That's where the data comes in, again trickle feed. So from all the different Hilton hotels around the world, the data comes into that single database server, right? And then every night they will process the analysis server cube there, the one with on the left side analysis server, which is COLPF MS7. So MS7, let me call that MS7. The MS7 is a very small server which is meant for cube processing. So the data comes in to the database server, they take the data, process the cube, and then what they do is they use the snapshotting technology, EMC snapshotting technology, to copy those, make a snapshot of those cube files into the MS8 server. Because if you remember, MS8 is their main cube server where data will be taken from by all the analysis server, right? So every night after the cube processing is done, they will make a snapshot. But they want to have high availability. They don't want, during the cube processing or during the snapshotting, they don't want to have any interruption to the users. So what they do is they basically create on the MS8 server, they create another set of the cube files. They don't overwrite the existing cube. They create another cube file. So any request already running will be using the old cube that's already there. But any new request, so as soon as they process the queue processing is done, they make connection string changes or whatever automatically to point any new request to point to that new queue. But the old request still running, still be connected to the old queue, because the beauty of that snapshotting technology. So they connect to that, and at some point they will flip the roles. They'll make everything go to the new queue until the next day. So that's how, even though with such big cubes, they're able to get that high availability. They're able to get the performance without any problems by using this snapshotting technology, and by able to scale out multiple reporting servers and analysis servers without compromising on performance or availability by using this technology. So there is also, go to the white paper, the link I mentioned before. There is also another link that Kevin told me that there is a link available with more details on the architecture. I'll try to find that. I'll send you all when I get that one from Kevin. But it's very, again, if you see, all the servers are Windows 2003 and SQL Server 2005, and we are still able to achieve better performance and scale up and scale out better. All right. So next one is analytics before OLTP. So, we all know, like, when we are talking about cubes and running reports off of the cubes and processing, that there is some time lags, right? So as soon as the data gets, like we were talking about the Hilton architecture, that the data gets in, then you process the cube, then you present to the analysis server so you can generate reports off that. But anybody know Stream Insight here? Anybody worked on Stream Insight? Okay. So basically, it's a concept of Stream Insight, and again, I don't have the customer name here, but remember that millisecond latency I was talking about? This is how we can achieve by using the Stream Insight. What does that do is basically, before you even go and start, getting the data into the OLTP server, then process the data into a queue, before even you do that, you tap some of that. So if you see that, that is the Stream Insight server, the one in the purple with the green arrows, a green box. That's the Stream Insight server, where you're basically, when the data is coming from those event sources, right? So before even it goes to the OLTP, we are tapping the data using those standing queries to retrieve the data from the server. So you don't have to wait for your cubes. Of course, you cannot do everything. It's not like a replacement for your analysis services, cube processing, or anything. But you may have some requirement to pull some of the data faster. You don't have you don't want to wait until cubes are processed, the data is completely trickled in. You don't want to wait until that time. Like, for example, pagers and monitoring devices. So you want to be able to get the data faster to those devices before even if the data was going into the OLTP. That's the analytics before OLTP. And Stream Insight helps you do that. There's actually a very good white paper on Stream Insight on SQL Server website. Actually, most of these slides, I have those links in the notes section. So I'll give you this slide. In the notes section, there are very good white papers, which I can't cover due to the time here. So you can go to that and look at Stream Insight. Stream Insight is a very good concept where it's basically, we know the traditional way is OLTP and then OLAP, right? This is like OLAP before OLTP, or analytics before OLTP. So some of the customers are able to use that Stream Insight technology to get the better performance with their large SQL installations there. Okay, so that's OLAP. Actually, we are going to also talk about some more strategies about how they how they use those technologies, about scale out and scale up. And let's talk about some of the OLTP technologies we have, OLTP case studies where they're able to achieve very large sizes without sacrificing the performance and availability. So there is one case study we'll talk about scaling out just one database. In one case we'll talk about scale up, how they scale up one database. And there are two case studies we'll talk about. There is no downtime allowed. We're talking about when you're talking about megabytes or gigabytes, yeah, we can achieve that. We can make sure that no downtime is there. But when you're talking about terabytes and petabytes, it's very hard to maintain. I mean, by downtime, I don't only mean the server is completely down. Anytime you're not meeting your SLAs, that's a downtime, right? So how you can do that without when you're talking about terabytes? So let's look into that. And there is also one case study I talk about 16,000 instances in one customer, 16,000 plus instances. So we'll talk about these individual case studies. Well, the very first one is our very own Microsoft CTP, Commerce Transaction Platform, where we chosen to scale out. Basically, if most of you may be using Xbox Live account, Zoom. So this is a commerce platform for when you have a subscription, when you buy something from a Zoom or Xbox Live. This is where all those transactions will be going to. Commerce Transaction Platform. There are 13 payment methods they use, 42 currencies across 65 localized markets. So it's pretty huge because it's one platform for multiple very popular technologies like Xbox Live, Zoom, and Windows Live. There are 5 DBAs maintaining this CTP. Wi-Fi DBAs, well, DBAs need some downtime too, right? They need some vacation, right? So, well. So basically, there are 2 data centers for this CTP with 5 web store clusters, 15 replicas. So all the data is replicated using transaction replication, snapshotting technology. There are 15 replicas. Why 15? Reporting for different, financial reporting, fraud, looking at any fraud things. So there are like that. So there are different departments have different requirements for looking at the data. So there are 15 replicas being done because again, so it's basically isolating or maintaining that isolation between the OLTP and reporting, right? So make a replica and start reporting off of that. The 220 SQL servers. SQL Server 2000, and these are all physical servers. We're not talking about virtual machines here. So CTP alone has 220. So basically, that's how scale out. 736 databases, that not including mirrors or secondaries. The main production databases are 736 databases across 121 terabyte of data files and 420 terabytes of storage. And we have 12 terabyte of monthly growth. I mean, you can imagine, right? Xbox Live, Zoom, it's pretty, there are a lot of transactions going there. So 12 terabyte monthly growth. Yes?
Which one adds more, Xbox Live or Zoom?
What do you think? Yeah, I mean, Xbox Live got to be the one, right? I mean, I'm guessing, but that got to be the one.
Zoom adds like 10 megs.
Okay, so 82 database mirror pairs for some mostly asynchronous mirroring, but there are some synchronous with auto failovers. 70 log shipping pairs and 400 replication subscription streams across 6 distributors. All this for one CTP, commerce platform. Well, this is one slide I just wanted to show because with this kind of monitoring is the key. I mean, everybody knows that, right? So this is one of SCOM snapshot for that specific CTP application where it's very important to know certain key factors, and SCOM can expose those. Like for example, how many SQL errors per second? What is your redo queue for those database mirror pairs? Because you have so many mirror pairs, and there are SLAs around how much data you can lose and how much downtime you can afford. So all that needs to be monitored, and SCOM is one that can help you, helping us to maintain this huge CTP application without major glitches. All right. Next one is a large healthcare. Yes.
I'm sorry. This previous one with
Come
no
on.
downtime error. At this point, I don't see anything there that I can see that is possible yet.
Okay, a good question. But in this case, CTP, our application, we don't have that requirement of no downtime ever. We still have, I don't know, 4 nines maybe.
Right.
Uh,
When you started, there was that,
Yeah, I agree with you on that. So there is possibility of downtime, but there are other customers that we're going to talk about which say that no downtime ever. And let's see how they can do that. They still use the same technology. They don't use anything magical there. They still use high availability provided by clustering, database mirroring, but they're still able to get that. Well, yeah, no downtime ever. Maybe too much to say, right? But that's what they want. But then again, it has to be measurable, right? So in one case, 5 nights is the 100% during the. We'll talk about that. We'll come to that. But in this case, this is our Microsoft technology, and we didn't have. Well, there is a requirement of I don't know how many nines, but we do have, and that's why we have so many mirror replicas and log shipping pairs and all that to provide that. But there is downtime there. I mean, it's not completely no downtime ever in this case.
So the question is planned versus unplanned downtime. Maybe is probably what you're.
Exactly. Yes.
Still planned downtime for patching, maintenance, and whatnot.
True.
When you're talking about.
Yeah. So no downtime ever unplanned. Let me put it that way. Right. All right. So next one. Any other questions on that one? About the no downtime. I know. We'll talk about more about how we can achieve that. Of course, we don't go fully technical and details into that, but it is possible. It is possible to get no downtime ever unplanned. Planned, yes, you need to have maintenance, you need to have patching. To be able to have no unplanned downtime, you need to have some planned downtime, right? So but we'll look at that. So this is a large healthcare provider. Again, I can't take the name there. They have a 17 terabyte OLTP database. They choose to scale up instead of scale out. And 10,000 concurrent user connections. That means if you go onto this server and hit an SP-WHO or SP-WHO2, it takes forever to get the 10,000. I mean, not all 10,000 are active every time, but their connection pooling is such a way that they have 10,000. You might have seen that, right? Some of you?
I've got about 6 online.
6,000? Okay. Yeah, and they use replication for reporting database, and then they use a SAN hardware application for disaster recovery. Because 17 terabytes, so in some cases you want to be able to get the faster data transfer. You may have to look at some third-party technologies like SAN replication to be able to get the data faster on the other side. So performance engineering is a part of their methodology. So before they make anything go into production, it has to be performing well. So they test, and test. So that is a key. So test to make sure that they are achieving the performance they need. If they're not, it's not going into production until it does. So performance engineering, their part at the methodology. And then at the application tier, they scale out. So anytime they need more load balancing or more performance at the application tier, they use they add the servers, and then they use the load balancer, hardware load balancing, just like the Hilton hotels we have seen, to load balance the connections coming in. But at the OLTP, at the database side, they choose to scale up instead of scale out. So anytime they need more power, more juice, more performance, they add more CPUs. And SQL, especially SQL Server 2008 or 2, you can scale up to 256 cores, I think. Yeah, I have a slide on that. But yeah, so you can scale up. You can start adding if your servers are capable of. You can start adding, and you can also do hot add CPUs these days. So without major downtime, you can add more CPUs and get better performance. And of course, as you see there, they segregated their OLTP and reporting. That's another key. So everywhere that's must. So you don't want to mix and match your OLTP with the reporting loads. That's one major reason for most of the time we see performance problems. So you need to always segregate those loads, reporting loads versus OLTP. And this is how they use SQL replication to do that, to segregate this OLTP with reporting. Again, scale up when they need. So that's the large healthcare organization. And then there is a security trading organization. Again, I cannot take a name here, but basically they do stock trading and things like that. So they are real-time, high transaction, low latency stock quoting. So when you're trading stock, you know how important that is to be real-time, and you cannot afford any latency. You need to be able to see the stock prices and be able to trade immediately. So it's very crucial. So that's how they have like over 500,000 business transactions during peak time, and 350,000 sustained at any given point of time. And they choose to scale out. They use 6 active SQL servers. They have over 1 million DML calls in every single database per second. 1 million DML, data manipulation, Basically, the moment you submit a code, it should be going in. If you make changes, they should be able to modify that. And all those data manipulation languages, data manipulation calls, 1 million per second. And with all that, the latency is under 50 microseconds. Knock on wood. So how they're able to do that? They're scaling out, and they use what I said, the SODA, service-oriented database architecture. We'll talk more details on that. But they're able to achieve that by distributing their load across the 6 active SQL servers. So basically the way they do is, actually in the next slide I'll talk about how they do that. So they basically send large batches containing multiple business transactions and insert into the large table, which is constantly read. They only have like 10 tables in the application, but they're pretty huge, and they're able to get very good transaction throughput, even with all those 500,000 business transactions per second and 1 million DML per second. Again, 5 DBS they have.
Can you give us details on the size? Because only 10 tables. I love the sound of it. That's absolutely fabulous.
Yeah.
Can you give us details on the size of
The size, let me see if I have size on this particular one. I think I don't have the size on this one, but I can get that.
I was just asking.
Yeah. Actually, yeah, I need to ask Kevin to see if we have any size information. But it's again security trading organization, so you can, and with so many 5,000 transactions coming in per second, they got to be huge. But I don't know exact details on that, but I'll get on. The way they do is they distribute an alphabetical split. So out of those 6 servers, like if you're talking about a MSFT stock, it may be in one of the middle servers. It's alphabetical. So they distributed based on the ticker symbols. They distributed the rows, the data into the 6 servers using alphabetical split. They use the DDR scale out. I'm sorry, I think I said SODA, but they use DDR, data dependent routing. We'll talk about that in detail, how the data dependent routing happens. But basically the way it is, like if you go inquire or look for MSFT stock code, or you're trading MSFT, it knows which server to go to. Out of those 6 servers, the data dependent routing routes the call in such a way that it goes to that one specific server where the MSFT resides, and that will be able to go. So that's how it's load distribution. They use simple commodity-based hardware, but they use high-performance SAN. Actually, they use solid-state disks in their SAN. So again, I/O, very good I/O throughput they will get. That explains why they are able to get under microseconds throughput, right? But they use normal commodity-based hardware. It's very mission critical. They require finite uptime and 100% during business day. So 5 nines, that's the unplanned downtime. So planned downtime. So out of the during off-peak hours, 5 nines, but during business day, they cannot afford any downtime. How do they do that? They treat their systems like mainframe operations, which means they have those 5 DBAs, right? You go to one of those DBAs and say, Mr. DBA, can I? No. That's how serious they treat their. Seriously. Change. There got to be a way to maintain your changes. You can't go in the middle of the day and ask DBA to make this change, make that change, right? It has to. You had to plan that. You had to control that, and that's how they treat their systems like mainframe operations. Absolutely, absolutely, no changes allowed during business days. Everything needs to go through proper controlling mechanism to be able to go into the system. Doing things like that. Seriously, I have seen when I used to be a DBA, I have seen like so many cases. Okay, can you run this script for me? This does nothing. It's just and then boom. So that's the one. So, and they use of course failure clustering for again. So they don't use anything very anything that's out of ordinary. They use simple our built-in high availability technologies and still are able to get 5 nines and 100% business downtime during the business day. Actually, Kevin told me during his presentation. So everybody knows failover clustering. So if there is a failover, there will be downtime, right? So Kevin asked these DBAs, how are you able to achieve this 5 nines with failover clustering? They say, because we never had any failovers. So we never had to. So yeah. Right? So that's also, they use database mirroring for the disaster recovery for high availability, and they use failover clustering. They have 250 miles between, so they use asynchronous database mirroring, not synchronous. So they get about 30 megabytes per second log generation, and they're able to do this. They're able to achieve these 50 microseconds, and they're able to handle these. Here, it's not just the size of the database, it's the activity. If you see that 1 million DMLs per second, isn't it?
Yeah.
So,
Just asking how big it was.
but yeah, but I'll still get those one, but that's
Because
how
it
it is.
really strikes me with
What's that?
it really strikes me with only 10 tables and large data sets. Your data types and everything have to be so tight because you go from a simple data type and change it just a little bit, you can quadruple your transaction time.
You're right.
I'm just amazed by. I love stuff like that, right? Where stuff really matters.
Yeah.
So I
And,
was just wondering how big it was, so I can see.
Yeah, I'll get you more details on that. And the next thing is BWIN. Anybody know BWIN? They're gambling, basically, is online gambling, sports gambling. Actually, if you want to bet on who is going to win Super Bowl, just give an example. So you can gamble. You can go gamble bwin.com, and you can go gamble. And who you want to know, like a soccer game is going on, and you want to bet on who is going to get the yellow card first. You can gamble on that. So they do all that. It's pretty cool. So they have 15 million page views and 980,000 unique users a day. People love gambling, apparently, right? 980,000 users a day. Again, 5 DBAs they have. And here I have some statistical information about the databases, like 100 plus SQL Server instances they have. And this is where they use SODA. So they based on services-oriented database architecture. Again, we'll look into those details more. So 100 plus SQL Server instances, 120 terabytes of data, and they have 450,000 SQL statements per second on a single server. So on any given single server, and again they have scaled out. They have multiple servers. On each single server, they have 450. Of course, because 980,000 users a day, so there got to be a lot of data, a lot of activity going on. 500 billion plus database transactions per day. That's how busy they are. Again, these are the guys who said no downtime ever. Let's see how they do that. Again, what's that? It is, right? Because they don't want to lose their money, because if they're down, people are not able to gamble, so they'll lose money, right? So
We lose money.
we lose, yeah. They want us to lose our money, but anyway, there's. So again, so they use the simple mirroring and log shipping architecture. They use a principle they use the synchronous replication, synchronous mirroring here from, and then they use the log shipping for second copy, and then they use something called OOPS database, log shipping with 1 hour delay. So if anybody makes, again, these are very crucial financial transactions. They need to be very careful about those. So if somebody makes any accidental changes, they want to, if they are aware of within 1 hour, they can go back and get their data. So they maintain that OOPS database to be able to go back in case it's needed. But something tells me they never had to go back to that, but it's there. Anyway, so again, so that's how, so they get the high availability using common built-in technologies within SQL Server. Nothing fancy, nothing out of ordinary. Within that, they are able to get the 5 nines, again, because their operations, the way they maintain their operations, they go through proper change control mechanisms and auditing and everything, so they're able to do that. And they use scale up and scale out, so they use basically SODA. Before, this is where our CAT team helped them. Before, they used to have everything in one set of databases, all the transactions. We helped them to do the services-oriented database architecture, where we distributed the data. We helped them distribute the data based on services. So they have one database for main financial transactions. They choose to scale up that one. They don't want to distribute that. So it's all financial transactions going to one set of databases, and they're scaled up. And all other application functions, all other secondary that are not directly related to finance, they all use service-oriented database architecture to basically distribute their functions across multiple servers. 2 data centers. They use synchronous database mirroring, which adds 1 millisecond per transaction latency, but they're okay with that. Again, they use replication for reporting, log shipping for DR. And here, actually, we learned something about how to back up a 2 terabyte. We helped them achieve this. They are able to back up 2 terabyte over the network within 36 minutes. Anybody tried that? You did?
Sean taught the class.
Okay, good. So basically they use multiple network cards with jumbo frames. They use 8 1 gigabit cards with jumbo frames, and of course they use the database compression. Without database compression, they got it to something around 2 hours for 2 terabyte. With database compression, they got it to 36 minutes over the network. This is, again, we're not talking about the local database copy. They take their backups and store them at a different location away from their data center, again for disaster recovery purpose, and they're able to do that backups. It used to be like 24 hours for 2 terabytes before. So we help them. Actually, there is a very good white paper on that, how they did that. You may have seen that. So you can go to that link to.
Is that 2008 R2?
It is 2008 R2. Actually, yeah, these are the ones that actually, as we speak, they are upgrading to 2012. Because of the downtime, uptime requirements, they're actually, because there are multiple databases, they're going into use the availability groups with 2012 to be able to achieve that, because they want those multiple databases to be able to fail over at the same time without any inconsistencies, so they're planning to use the high availability groups. So they are one of the many customers who are going into 2012 even before its release. And then again, they have a case study on the case studies website. You can take a look at that. And the next one, a retail application. Again, I can't take any name here. It's a retail. It's a big retail chain store. So they have 1,200 stores across the country. They use SQL Standard there with a 10 gig average database per store. And then 15,000 cache registers. They use the free SQL Express edition for those cache registers with about 10 MB database. And then 1 corporate server farm where they have the SQL Enterprise with clustering, DB mirroring, and log shipping. They use all the SQL Server analysis services, integration, reporting. They have about, as we speak, more than 12 terabyte database with 1.5 terabyte cube for their analysis services. They use merge replication. So basically, they have this pricing information changing at the corporate. Corporate has some products with some pricing information that need to be pushed to all those 1,200 stores. At the same time, each store can maintain their own local products. They price their own product. That data need to be sent back to the corporate. So they have merge replication going on between those two. This is actually one of our very big merge replication customer. And then they use service broker for all of the transactions. Again, because async, so they don't want to tie up, if all 12,000 stores starts sending transactions to that one single form at the corporate office, it's going to be very, there will be a lot of latencies and contention and everything. So they use service broker to be able to do that async without losing any consistency of the transactions. They'll be able to use a service broker to do this one. In fact, this is one of our largest service broker and merge replication project. They have 2 million products, 25 million accounts, 10 million transactions per day. Again, it's a retail. It's a very large retail chain store. So they have very large number of transactions going on, and SQL is able to handle that. Okay, so those are the case studies. Now let's talk about some of the nitty-gritties in there. Some of the how they are able to do that. How they're able to scale up and scale out. So when it comes to scale up, we have different, table partitioning is one of the very good scale. It is both scale up and scale out technology. Then the CPUs, I said now we can go up to 256 cores. I'll actually show you an example of how that works. NUMA, worker threads, these are all scale up. And then scale out, table partitioning, partition views, SODA, and DDR. So let's look at each one of these. So scaling up, Windows 2008 R2 can take up to 1,024 cores, right? But you need to know about kernel groups. Anything above 64, there is this concept called kernel groups, which is something similar to NUMA, but it's basically grouping up multiple servers, multiple cores to get the better performance with those huge number of cores. But SQL Server 2008 R2, the limitation is 256 cores, so it cannot go beyond 256 cores. Currently, the largest x64 machine that we are aware of is 96 cores, and in an Itanium, it's 128 cores with hyperthreading 256 cores, 256 hyperthread, and of course the maximum memory is 2 terabyte RAM. So the largest server we know as of now is a 256 core server for SQL Server 2008 R2. And it looks like this. Anybody seen this? And if you notice carefully, look at the CPU usage. All those 256 cores are busy. You know why? This is our lab server. This is where we tested that 1 terabyte load in 7 minutes. So while that 1 terabyte load is happening, all the cores are busy. This is why, even customer machines can do that. But you don't want to occupy all the cores just for loading, right? So that's why they throttle it down and still get 30 minutes in 1 terabyte load in 30 minutes. But in lab, we could prove that 1 terabyte we can get in 7 minutes. All right? So basically bulk load. So all these cores are busy doing the bulk loads. 256. It's 256. Yeah. 16 times 16, right? Yeah. Thank you. Yeah. All right. So that's scale up. So scale up, you have this capability of symmetrical multiprocessor systems where you can scale up to 256, and your storage system you can scale up as well with new technologies. So we can do SSDs and all that. Now scale out. How do you manage? We're talking about 80 terabyte database, 100 terabyte. How can you manage that? And how can you back up a petabyte? How you build an index on a trillion row table? Anybody? How can we do this? Is there any magic? Huh? Partitioning. Break it into manageable size pieces, right? Again, there is nothing very out of ordinary, nothing magic to it. Again, partitioning, that's helps you there to manage that. You don't have to really back up that petabyte every day, right? It's not that each and every byte in that petabyte is dynamic and being changed. So you can do partitioning to be able to back up the most recent partitions, most active partitions. Same thing, you can rebuild indexes partition-wise to be able to achieve this without major downtime and without any performance degradation. So, when you have a big table, you can partition. Those P1, P2, P3 represent partitions, and then you can have indexes on that. So you can individually back up the, you can have these partition on different file groups, so you can take file group backups. When it comes to indexing, you can rebuild indexes partition-wise, choose a few partitions a day at a time and then rebuild them. So all that is possible with partitioning. Now, what if, okay, so the partitioning, you can do like, let's say you have a year worth of data in a table. So maybe you can do partition by month or, even partition by day. But then what if you have to, as the data increases, you want to have less, like a yearly partition as opposed to a monthly partition, or monthly partition as opposed to a daily partition. You cannot mix those partitions within the same table. In that case, you can have multiple tables. So you can have, you can split the data, again, break it into, expand it, take it into multiple tables, have one table with yearly partitions, old data, and most recent data put in a monthly partitions or daily partitions. So you can mix and match, right? And then you can have a partition view on top of that. So you can view the data, you can update the data as you please. So partition views in combination of partition table helps you do that scaling out of your big tables. We're talking about 20 terabyte tables, and then if you still want to go beyond, like, okay, so you now have all the data within the same database into multiple tables. But then you may have that old data which may not be changing, which may be relatively static compared to the new recent data. You don't want to back that up every day, do you? It's static. So then you can also go beyond just tables. You can go into databases, right? So you can have multiple databases so you can have all that old data that is relatively static in its own databases, and then all the recent data in its own in a different database, and then you can have cross database partition views to query the data to make any changes and modifications to the data, right? So from a single table partition, we expand it to multi-table partition, and then we expand it to multi-database partitioning. What next? Yeah, I expected that. But then, yeah, Sean knows some of the negative, things about that. When you're talking about intra-server queries, we are talking about. I mean, it's not that you cannot do. You can, but we are talking about linked servers, and the security problems associated with that, and all that. So this is why, in case of data warehouse, we have our very famous PDW, parallel data warehousing, right? So when you have to distribute across multiple tables, multiple databases, when you are going beyond one server, PDW, parallel data warehouse, for your data warehouse projects, and some of the projects we talked about, some of the data warehousing, they use PDW to achieve that, the huge terabytes of data to host the data without sacrificing the performance. So this is one of the 10-node HP DL380 G6 parallel data warehouse. Gives you very better performance, and without sacrificing on performance, it will be able to host terabytes of data. Now, what if this is not enough? You're going beyond this, and these 10 servers are not enough. Then we go into this hub and spoke model, where we have multiple PDW servers, where you have one per different type of functionality. You can based on that, so it goes into hub and spoke model. So when it comes to data warehouse scalability, PDW and hub and spoke model can help you. But what if relational data? So we talked about some cases where we have the relational data that is going beyond terabytes. How you can scale out that? That's where the famous SODA comes in, services-oriented database architecture. So basically, again, the concept is to be able to scale out based on the function, business function. It can be a business function or a user function. In case of, we talked about the BWin. BWin did by business function, right? So you have all the financial data in one server, all the different, HR, payroll, all those are distributed into individual servers based on the service-oriented database architecture, and then they're able to distribute their load, still be able to maintain all the data without sacrificing on the performance with the same, without having any availability issues. So service-oriented database architecture, that's one major, and of course, if you're talking about things like the social sites, they may be doing by user function, right? Or for login, they use one set of servers, charting, email, pictures. So all that, so that's all can be done using SODA, service-oriented database architecture, where you go beyond. When you're thinking about going beyond one server or one set of servers, you should think about distributing based on the functionality. I mean, there may be some times where you have to interact between these servers, right? And maybe HR and payroll go together. Sometimes you need to have some queries, some updates that can affect both servers. But most of the time, you're able to distribute the load in such a way that you will be able to get better performance without sacrificing, able to have huge chunks of data without sacrificing performance by distributing. So distribution, so data distribution, load distribution is the key, and SODA is one of those technologies. Again, this is nothing like built in. It's a technique that you can use, and our SQL Cat team helped a lot of customers to do this, including the examples we saw, BWin, to of course, and you may have some common database for shared tables. There may be some data that is shared, so you can use a common database, but all the major functionality you can distribute using SODA. Then the data dependent routing. So the security trading organization used this DDR. Again, it's relatively simple here. So basically what happens is one of the examples of this. So you have, let's say, number one there, user login. So from the web tier or app tier, user is logging in. What happens is that login goes to the login server towards the bottom left there. So it goes to the login server, and what that does is it gets the connection string. So you have a hash table where you have the login and connection string mapping, login and the server mapping. So maybe let's take a public, the social sites. So based on the login, you may want to, actually there is one good example Kevin gave me on this. There is this a band, Stop, what is it? Forgot the name of the band, but they have very famous video that they dance on treadmills. They have a series of treadmills. I don't know if anyone has. Yes, okay, go. So this is one of the examples. They use DDR to be able to, because that video was so viral, so popular, that their servers started melting down when people started all logging into and watching that video. So they it's one of our SQL. It's on SQL. It's hosted by SQL Server. So one of our engineers was there with the video hosting company. So they immediately they were able to use, because they were using DDR. They were able to just add another server, put that video on that. So they were able to distribute that within seconds. They were able to distribute that load to that one single server without sacrificing performance for others.
Are you telling me that video got its own server?
Uh-huh.
That's lovely. I love that.
Yeah. So that's the beauty of DDR, because again, so based on the login, based on certain credentials, so as you see, as soon as the login comes in, the login goes to a login server, and there will be a mapping. In the hash table, you can also do a hash table, because the login mapping may not change often, right? There may be new entries, but the login and which server it needs to go to may not change much. So they can put it in a hash table which is very quick. You can get it immediately within microseconds. You can get the login and the server mapping information. So the next second, the connection knows where to go. So it doesn't have to hit each and every server to see where the data resides. Based on the login, we route. So it's a data dependent routing. So based on the data request coming in, you route the connection to the appropriate server. So you're distributing the load. And like given that example, so you'll be able to scale out as you need. So if anytime if any server is too busy, you can add another server, see what is making that server busy. So you just make the simple change to the hash table, and you have you just have solved your performance problem. So like that. So SODA, and so when it comes to data warehouse, PDW gives you, PDW and hub and spoke technology gives you scale out. When it comes to relational, SODA and data dependent routing gives you those same thing. And then when you're talking about scale up and scale out within the servers, we are talking about partitioning. So all these partitioning and isolating your reporting and OLTP loads. All these technologies, database compression, not to forget that. So all these distributed partition views, all these technologies. Again, there are nothing there's no magic here. So you can get your servers, you can scale out. Again, like Sean mentioned, there is no such thing as this is you reached your end of you reached the threshold of something. You can scale out to any extent, as you see these examples. You can scale out. And you'll be able to get these with using most of the time built-in technologies, in some cases going beyond built-in technologies like PDW or SODA and things like that. You'll be able to achieve this better performance and able to host terabytes, petabytes of data with using your SQL Server. So like I said, database size, transactions per second, concurrent users, none of those. There are no limits on, okay, this is the end. You cannot do more than this for SQL Server, all right? And SQL Server is fully enterprise ready, mission critical. You can use it for mission critical applications. You have flexible HADR options to get that availability, 5 nines or whatever, without sacrificing on the data or on the performance, all right? So that's the end of the story. Any questions? Any additional questions on? I know, Sean, I need to get you some details on the database sizes. I know you're interested in. I'll send it to everyone. Anything else? Anyone? Yes?
When would it be more appropriate to use SODA over DDR?
Good question. So the question is, when will be more appropriate to use SODA over DDR? Again, the famous consulting it depends. Because, it depends on what where you have your bottlenecks are. If you're trying to distribute by a business function, then, SODA may be a better option for you, because if you are able to distribute by business function or login function. If not, if you want to distribute the data just as is, you don't have any real way to isolate or differentiate the data, maybe DDR may be a better option, because then you'll be able to distribute the load and then use the login mapping to be able to send the data appropriately. So it all depends on, it can sometimes, in some cases actually it's a mix and match. Even BWin, it's but financial data they scaled up, which is SODA, but then they use DDR to be able to send the data to multiple servers from the same for the same business function. So it can be a combination. It need not be just one. Any more? Yes.
I may be a little bit out of date here. Is there any capability within SQL Server to allow single instance with multiple servers?
Single instance, multiple servers. No. So the question is it possible to have one instance across multiple servers? The answer is no, you cannot. So you cannot distribute one instance with multiple servers. But then, so that's why, so when it comes to SODA, where within, the single instance may have one database or multiple databases, you can distribute those databases across multiple instances, multiple servers. But you cannot distribute just one instance into multiple servers. Any more? All right. Thank you once again, everyone. Thank you. So I have this slide deck. I'll be handing over the slide deck. There are so many links and there are notes within. Anytime if you have any questions, if you want to know more information on specific case study or specific technology, specific technique, please, you know where to find me. So send me an email.
I have a question.
Yes.
Now that we have two MCMs out here, how do we get it? How can we prepare?